All right, so pull up your data set, the one that we were working with last Wednesday, the belief ratings set, and then also and then pull up the copy of that annotated output I sent you. So I had suggested people take a look at this. Four hands, show of hands, who looked at it? Timid hands. See, CJ thinks I'm trying to trick him or something like that. I'm like, hey, make sure you look at this before class. He's like, it's probably a trap. Okay. For those of you who went through, took a look at this. Was this helpful to have? So basically, this is just like a hand copy of my notes with sort of stuff going down through. I mean, is this a useful resource for this? Okay. So as a recap, and it's been a while, right? Remember what we have is we have responses to 4 different vignettes about a hypothetical survivor of some type of traumatic event. And what we have is we have between subjects factors is this class variable. We have negative, people who have generally negative beliefs about trauma and its impact, benevolent people like, oh, things are pretty good, and then interpersonal, people who are specifically reporting some sort of interpersonal concerns with the effects of trauma, that sort of people might be hesitant to develop a relationship with someone, or would have a coworker or someone who's experienced significant trauma, right? And so we went through, screened it. These data are terrible, but we ignored that piece of it and went down through and just ran our between, by, within, or mixed factors ANOVA model. Nick, can you remind us what we found with that mixed factors ANOVA model?
Yeah, we found some support for differences in the vignette ratings as well as in the like both within and between, and there was also interaction or moderator effect, although the looking at the mean differences were very small.
Right. So we have 2 conditional effects, right? To use tomorrow's words, very good words. Conditional effect of rating, right? And basically, we're just looking at this rating effect. This is saying that based on the data we've collected, we would reject the null hypothesis. We have evidence against the null that mean levels of ratings are identical across all vignettes, right? So this is telling us that across repeated assessments, we're seeing some difference in the pattern of means, right? And then for these data, we also went through and down and found a group level effect, right? And this is saying that if we collapse across repeated assessments, we're seeing differences in overall willingness to provide friendship across these different classes, right? But that's also a conditional effect because what we found up here is a between, by, within interaction. Okay? CJ, can you tell me what that between, by, within interaction means?
It means that they're like individual relationships or associations with the likelihood to remain friends are dependent on each other.
Kind of getting there, right? What we're saying is we can talk about it a couple of different ways. Probably the easiest way, right, because the focus is on this repeated assessment, right, is what we would say is the ratings of willingness to provide friendship across these different vignettes depends on what group we're in, right? So it's not the same pattern, right? So the pattern of effects isn't across these individual vignettes, is different for the negative, the benevolent, and the interpersonal groups somehow, right? And so, as Nick mentioned, this is an interaction effect, right? We're saying that the difference in or the variability or the pattern of responding across these repeated assessments is dependent on group membership, right? And when we're doing these types of designs, this often is really what we're looking for, okay? Questions about this? We sort of up to speed on at this point. Okay. So what we then need to do is we need to go through and we need to decide, okay, so we have an interaction, how are we going to go through and talk about that? We took a look at our means, and boy, those look pretty big, right? Besides what's also going on with this graph here. And why does it look like we have such a huge difference?
Because there's not that many people in the negative group.
Okay. There's less people in the negative group. We still have a decent number of people. What's going on with the y-axis here?
Oh, sorry. It's actually just a very small amount.
We're super zoomed in, right? But what we're finding is even when we're seeing just these very, very minor differences in ratings, we're still seeing evidence based on these very, very powerful analyses that these ratings are differing across individual groups, right? And so with that interaction, now our job is to say, how are we going to go through, how are we going to tease this apart, right? So we identified 30 possible pairwise tests within this interaction that would be interpretable. No one wants to do 30 possible tests, right? That would be really almost always going to be impossible to try and make some sense of what's going on. So we have to have a game plan, right? And so what we're going to do is we're going to pretend that before we did this, we had expected within each group, overall, people to rate, be less willing to provide friendship to survivors of combat trauma relative to civilian types of trauma, right? And so we're going to go through and pretend that we did that a priori, not after we did it, like for this example. Like, don't do that act after you done it in real life. But so we've got 3 within subjects contrasts that we're going to look at per comparison rates, right? So this is going to be 3 contrasts that we're looking at within the negative group, within the benevolent group, within the interpersonal group, comparing our combat ratings to all the combination of the other 3, okay? But then, as we're looking at this, we might say, well, after I've looked at this, I might be interested in whether or not, looks like the benevolent and the negative class, the benevolent and the interpersonal class are basically doing the same thing, right? These 2 classes are probably not differentiable from one another, at least on this, but the negative class looks like it's doing something a little different, right? So what I'm going to do is I'm going to say, in addition to my 3 a priori contrasts, what I want to do is I want to go through and I want to take a look at, for each vignette, do I see differences in the negative relative to the combination of the interpersonal and the benevolent classes, right? And so I've got 1, 2, 3, 4, exploratory contrasts that I'm going to run. And now I need to figure out how I'm going to control for that. I need to go through, because these came up after I looked at stuff, right? After I had scanned and ran in my head all possible comparisons, then I came up with this genius idea of contrasting the negative group from the other 2 groups, right? So I need to do something to account for that, right? And so what we did is we decided to hijack 2E, right? And so what we did is we say, well, what am I going to set my R at? Well, if I set it at 5, I'm going to get 10 comparisons, actually maybe 12 in terms of possible pairwise comparisons in here. 10 is probably not enough. Hit R is equal to 6, that gives us 15 comparisons. That's a little conservative, but this is all sort of exploratory follow-up stuff like that. I'm comfortable with that in terms of stringency and control, so I'm going to do this. Now I have to determine what my degrees of freedom are going to be. Well, what I'm going to do is, again, I'm just taking a conservative approach, right? So in terms of my pairwise contrasts, I'm going to say, in terms of pairwise effects that I was looking at here, the negative and my interpersonal, those are my 2 smallest groups, would give me degrees of freedom of 127. So that's what I'm going to set that to and just be. So again, this is super conservative, but it's also completely exploratory, right? So I'm sort of doing due diligence here, right? So if we set R equal to 6, degrees of freedom 127, this gives us a critical Q value of 4.10. What's nice is we know that Q holds a direct relationship with T, and if our critical Q is 4.1, we can translate that, we can take that divided by the square root of 2, gives us a critical T value of 2.9, okay? And so what I'm going to do for these exploratory tests is I'm going to go through and I'm going to run my contrast. I go normally run contrast. What I'm going to look at is whether or not my test statistic is greater than 2.9. If it is, I can claim evidence for a possible effect, controlling for given at 2 key less than 0.05. If it's not, I say, well, I didn't meet the threshold for something that's an interpretable effect here, right? And this is how I would think about this, right? Because we're trying to move away from this idea of significant, not significant, but it's hard to do that when we've got corrections. Basically, I would think about this as, what's my threshold for sort of saying, yeah, I'm going to go ahead and sort of make an interpretation on that, right? Okay. People sort of kind of following me up to here in this process. Questions about what we did or why. Okay. So then what we did is we went down and we started running our contrasts. And these are my notes for each one of the contrasts, right? And again, what we've got here is we're just going through, we split the file by class. So again, what we're doing is we're comparing willingness to provide friendship for hypothetical combat survivors versus all other vignettes, specifically within each individual group, okay? So we split the file by class, and then we're just running a one-way repeated measures ANOVA individually within each one of these classes, which is going to give us output that we can go through and run our contrasts here, right? So again, this is for our negative group, setting up our contrast, got our value of our contrast, using our formula to get our test statistic, our p-value, s-value, Bayes factor, confidence interval around my value of my contrast, and then an effect size here, right? So I've got 4 different vignettes. What I'm doing is I'm just looking at the pooled variance of these ratings, get a pooled variance estimate, take the my pooled standard deviation, value of my contrast divided by my pooled standard deviation, gives me an effect size here. Okay. People kind of see what we did, how we approached that within subject's contrast for our negative group. Okay. And then what we're going to do is we're just going to do the same thing for the benevolent group, same process, and then the same thing for our interpersonal group. Okay. So all we're doing is we're just saying, all right, we know that the impact, or sort of that the pattern of responses to these vignettes differs across individual classes. And so if we summarize this down at the bottom, and so we know there's a lot of different ways this can happen, but one of our hypotheses might be that, boy, so this within group contrast, this the magnitude of this contrast might differ depending on which group we're talking about, right? And if we see here, we kind of see this. We see that the contrast, the difference in sort of willingness to provide friendship for hypothetical survivors of combat versus civilian trauma looks to be a lot bigger for our negative group relative to these other two, right? And so I might start to hypothesize that, well, part of what's going on in this interaction is that we're seeing a much larger reluctance to provide provide friendship to hypothetical survivors of combat relative to other types of trauma, specifically for this negative group relative to the other two, right? Now, we don't have any sort of individual test across these things, but our interaction tells us that there's differences in there somewhere, and so this is one way we might try to sort of look at it and qualify it in a way that makes some sense, right? So here, I mean, my absolute difference for the negative group is over twice what it is in these other two groups, right? All of these we have strong evidence that there's no difference, right? Based on our p-values and our Bayes and our s values, but our effect size is saying that, boy, we've got something that's approaching a medium effect here versus something that's down in the small range for the other two, right? So again, thinking about what this means for understanding the interaction of repeated assessment with our group level stuff, it looks like specifically within this negative group, we're getting a much bigger discrepancy in terms of where they're at with combat survivors versus civilian trauma, as opposed to the benevolent interpersonal group. Okay. Is that coming together for people? Questions about this, or the kind of how we're thinking? This is the biggest thing with these types of designs, is figuring out how do I go through and tease this apart in a way that makes some sense that I can talk about. Questions? Okay, cool. So what we're going to do now is we've got this other piece, right? we also went up and we had said for our exploratory analyses, what we're going to do is we're going to look at negative versus benevolent and interpersonal at each vignette rating, right? And what type of contrasts are we talking about here? Chris?
We're just gonna do an ANOVA?
Yeah, what type of an ANOVA?
One way.
One way, within or between?
Between.
Between, right? So what we're going to do is we're going to treat each one of these repeated assessments as its own outcome, and we're going to compare negative versus interpersonal benevolent at each time point, okay? So what we're going to do is going up to our sets. Go to my data set. And this is the data set that we're working with before. And what I'm going to do is I'm going to go to analyze. We can go to compare means and go to one-way ANOVA. And I'm interested in looking at ratings for friendship, or excuse me, motor vehicle accident, combat, assault, and disaster. Okay, these are the 4 outcomes that we're working with. And what is my factor variable, Sean?
Class.
Class, right? So this is the difference that we're looking at. But, so for our within subjects contrast, will SPSS do within subjects contrast for us? Nope, that's all hand calculation stuff. Will it do between subjects contrast? Absolutely, right? So what we're going to do is we're going to go to contrasts. And we're going to enter, so negative is our first group. What's our weight for our negative class? We're comparing negative versus the combination of interpersonal benevolence. Yeah. Negative one. And we're going to say it's negative because we think that the negative group is going to rate lower than the other 2. So I'm going to hit add, and I'm going to say 0.5. 0.5 for my benevolent, 0.5 for my interpersonal. Add that, and what I've done is I've just set up a contrast that's going through and going to take a look individually at each one of these. Okay. Options, ask for descriptives, homogeneity of variance tests, just to see if I've got violations of homogeneity of variance there. I'm going to hit continue. I'm going to paste this, right, so you can see what this looks like. Now, if I had a number of different contrasts, SPSS is kind of bulky in terms of this. If I wanted to put in another contrast, I can go through and, oops, I could just copy that. And let's say I wanted to run a second contrast, just comparing my benevolent and interpersonal, right? Well, if I wanted to do that, what would my contrast codes be?
0, -1, and 1.
-0, -1, and 1, right? So if I wanted to look at that, I would just say, okay, 0, because my negative group isn't in here. And then I would say, we'll say benevolent is the next one. So I would say, oh, let's give that 1, and let's say -1, because I feel like interpersonal class is going to rank below that, right? And then now it's going to give me that contrast too. We're not going to run that because that's not part of what we're asking for, and I don't want to get confusing, but just remembering that we can go through and manipulate that syntax to go through and give us some stuff. Okay. So I'm going to go through and run this. So again, what we're going to do is this is going to give me a between subjects contrast, comparing negative versus the combination of interpersonal and benevolent at each one for each one of our vignette ratings. Okay. We go through and run that. And let me so this work here. Okay. And so this is what we're going to get. It's going to give us, first off, it's going to give us a table of our descriptives, right? This is just looking at mean ratings, sample size, mean rating, standard disaster. Is a nice way to go through. This is a resource this for other stuff we need to do, right? Then we go down, we're going to see a homogeneity variance test. Tomorrow, what am I interested in here in terms of homogeneity variance stuff?
It shouldn't be significant because if it is, that means we're
Right? And so again, what we're hoping for with the Levine's test, we're hoping for something that doesn't provide strong evidence against the null hypothesis, right? Because the null hypothesis is that population variances are equal. And so what are we seeing within sort of this, within this output?
We are violating that assumption in every group.
Yeah, so for every single one of these contrasts, probably the safest thing to do is just assume that we violated homogeneity variance, right? And Howell makes the argument that you should always just interpret corrected tests anyway, right? So even if you don't, like, just because it's going to be more conservative, and if you really have it, if their population variances are all equal, then they're just all going to be, and it defaults into the sort of standard test anyway. You don't have to do that, but it's an argument that you'll see made, right? So, but definitely here, when we get down to our contrast effects, we're going to go through and we're going to want to make sure that we're looking at those individually, okay? Now down here, we have an ANOVA table. Are we interested in this ANOVA table? What do you think, Sean?
No.
Yeah, why not?
Doesn't really tell us, it's not answering any of the questions that we have.
Yeah. This is just something that SPS is giving us as part of the output, but we don't care, right? We've already run our omnibus tests, like and these are the analyses, the contrast that we're going to run anyway. So this really doesn't, at this stage of the game, this is just something that happened to sort of be tagging along with the stuff that I'm actually interested in, which is down here, which is my contrasts, right? Always want to take a look at your contrast coefficient. So we have our negative class with a weight of -1, 5 for benevolent, 5 for interpersonal. Is this what we were hoping to happen, Sally? Yep. Okay, good. Always want to go through, because otherwise you start interpreting things, but you realize that you screwed up your weights, and then you're in a mess, right? So as we go down through, okay, Alicia, so in our contrast tests, are we interpreting equal variances assumed or does not assume equal variances? Does not, right? Because Tamara pointed out, we already had, it looks like we have violations of homogeneity variance, right? So we're going to assume that we can't interpret just our typical thing, so we're going to go down through, take a look at equal variances not assumed, right? And within that, Alicia, which one of these contrasts looks the most promising?
The friendship combat.
For combat, right? Which is not surprising given what we saw in that graph, right? We saw the greatest discrepancy between negative and the combination of interpersonal and benevolent for that combat rating, right? So it's kind of consistent with what we saw. That was probably why we elected to do this in the first place, right? So we have a p-value, assuming equal variance is not assumed, of 0.008. Chris, what do we make of that?
Not a whole lot as of right now.
Why is that?
It's a follow-up test, just because the samples are pretty discrepant.
Okay, samples are pretty discrepant. What else did we do before we decided to jump in the middle of these exploratory tests?
We also saw that there was like covariance based on the different groups, like the actual vignettes plus group. There was an interaction effect.
Okay, so yeah, there's an interaction effect. Yeah. So the pattern of means depends on the group of stuff, but this is kind of what we're digging into here, trying to tease some of that apart. What did we do before we decided we were going to jump in the middle of some exploratory tests? Tukey, right? And CJ, what was our Tukey, our critical Tukey that we decided that we were going to compare these exploratory contrasts against?
2.9.
2.9, right? So what we said is we're kind of on a fishing expedition here, right? one of you guys had asked me about fishing expeditions, whether that was okay or not. I think it's fine as long as you let people know what you're doing, right? And we're saying, yep, we went through and we decided to go on a fishing expedition. We saw some stuff that looks like it might be kind of interesting, so just given our general knowledge of this, but what we don't want to do is just cannibalize on random chances, sort of identify the stuff that's the farthest away and then claim that we found something, right? So what we're going to do is we're going to say we're going to set far more stringent criteria for claiming an interpretable effect than we would at just per comparison rates, right? And so we said 2p equals 0.29, right? So Ignacio, can I, am I able, if I'm playing by the rules that I myself set up, am I able to identify this as an interpretable effect or something that passes sort of my criteria for interpretation?
I'm not sure, because the significance is 6.
Okay, my p-value is 0.008, right? What do you think? You were shaking your head, CJ.
No, 'cause it's less than the
Yeah.
2.0.
I look at my test statistic here. My test statistic is 2.765. That's not exceeding sort of the threshold, the benchmark that I set up to say, hey, just as a conservative estimate, this is what I'm going to have as a threshold for identifying this as sort of an interpretable effect, right? So, is anybody bummed by that? He's like, you're the one, it's your fault, right? Yeah, right, but if we're doing this, but I mean, boy, normally, I'd be pretty excited about that in terms of evidence against the null hypothesis that ratings of willingness to provide friendship for my, in my negative group is equivalent to that of my other two groups, right? My test is giving me what looks like pretty strong evidence against that, but it's not exceeding sort of the threshold that I said is this is something that I'm going to make a strong interpretation on, right? And this is why it's important to, before you just post hoc correct for everything under the sun, if you do that, you're going to be bummed out because you're going to have far too stringent a control on things, and you're going to be controlling for tests that you wouldn't want to sort of go through and interpret anyway, okay? Now, this effect didn't sort of surpass sort of the very, very stringent threshold that I set as something that's interpretable. We're probably not just going to ignore it and say, well, we tried. If I had to guess, I think there probably is something there, but I have to be very careful about how I talk about this, right? You know, I went through and here calculated a 95% confidence interval using my value, my contrast, my standard error. And here I just used the critical value for T with the degrees of freedom here, right? So my 95% confidence interval says that the difference in friendship rating between my negative group and the combination of my other two groups for hypothetical survivors of combat ranging anywhere from about 0.2 of a point to about 1.3 points, a little over 1 1/3, or about 1 1/3 points. Low end of that is 0.2 of a point on a 0 to 8 scale. Is that meaningful? I don't know, maybe not. But again, taking into context that that this entire study pulls hard for socially desirable responding, right? My effect size is actually pretty good, 0.645. I mean, you're saying that my best guess is that my negative group is rating is about 0.65 standard deviations lower than the combination of my other two groups on willingness to provide friendship, right? So, kind of a bummer, right? Because I got something that looks like it could be an effect. But I have to realize that the reason that looks like it could be an effect is because I eyeballed that graph and cherry-picked the thing that was the farthest apart, right? So my penalty for doing that should be pretty stiff. Now, could I have made different choices that might have decreased the stringency of my test? Yeah, probably, but at the end of the day, if we fall on one side of the thing or the other, so we're not going to make too much of a difference there. But but needing to be careful about how we talk about things, right? We don't want to say, oh, this is the threshold for sort of talking about something, and then we don't meet it, and then talk about it anyway, right? Have to be consistent with this stuff, okay? So what we found here is we found among our within subjects contrast, we found fairly convincing evidence that within each class, people are systematically rating combat survivors lower than the combination of the other three vignettes. And that contrast, that those differences, look to be strongest in which group? The negative, right? And this is kind of where this is sort of the essence of our interaction effect, right? We're seeing lower ratings for the combat versus the other three, but it's particularly strong for the negative group, right? This is where that interaction, or at least the way we've put it together, that interaction comes in. It also looks like across subjects, or across groups, we really don't have super strong evidence of systematic differences for our MBA, our disaster, or our assault vignettes across groups. Looks like there might be something specifically for combat, but at this point, it's a little bit ambiguous, inconclusive, given that there's a possibility that what we did is we just kind of capitalized on sample specifics responding here. How are people feeling about sort of our approach to going through and kind of pulling this stuff apart? Is this the only way we could have approached this? No. There are an infinite number of ways we could have approached this, right? So this is why it starts to become important to have a good game plan before you jump in the middle of stuff, because it's going to give you a framework for how you go through and talk about follow-up tests and interpretations and things. All right, so how do we put all this together into something that maybe makes sense in sort of trying to make the determination of this? All right, here we go. In terms of our omnibus interpretations, we didn't go through the inpatient depression one. Again, I'm going to have a screencast that basically goes through that example just as a screencast, so you can walk through that just as a different example of what it means. But if, as you'll see, what we find is strong support for a group by session interaction. Results suggest that reduction in depressions over the course of intervention differ by treatment, right? That's just a general interpretation of the interaction effect, right? Same thing with our vignette study here that we're talking about. Results of a 3x4 mixed factor ANOVA model with repeated measures on final factor. So this is a nice way to describe things because it tells people specifically what the structure of your design is, so that everybody kind of understands what's happening. Provided modest evidence of a class by rating interaction. Within between subjects affecting these data suggest differences in willingness to maintain friendship with hypothetical survivors of traumatic and non-traumatic events may depend on pre-existing beliefs regarding the impact of trauma, right? So just kind of putting together and talking about that interaction. And again, here is just the interpretive benchmarks for Bayes factor. Oh, okay. I just wanted to be careful. So even for this, that we went through and wanted to sort of make interpretations about, sort of some different ways to go through and think about this and sort of being judicious and sort of how we're going for talking about strong, convincing evidence. So again, this is in your calculators when we're talking about percentages, likelihood, and things along those lines. That's just pulling some of this stuff together. Okay. So talking about our within subjects effects, we kind of did this already. Traditionally, sort of the idea is taking that within groups error term from your overall omnibus test and using that for your within subjects contrast. The problem is we have violations of assumptions, it throws sort of our error terms all over the place and things like that. And so what Hal recommends with our improving these interactions is going through and running a one-way repeated measures ANOVA across individual groups, or looking at paired sample t-tests at each level, right? Instead of hijacking the error term from your overall mixed factors ANOVA and running stuff from there, going through and breaking things down by groups, which is what we did, right? Between subject stuff, we can look at independent samples at each level. This is just kind of an extension of our between subjects analyses. What we're doing is we're giving up degrees of freedom sort of from pulling from the overall effect. What we can do from the overall analyses is pull contrast-specific error terms. Gives us more degrees of freedom, but it's computationally intensive, and you got to report things, and then if you have violations, then it starts to question whether or not that is a good thing to do. So what these slides are doing, and what Hal talks about, is from the traditional approach to ANOVA, right? From like a full experimental tradition, right? Where we're running randomized designs and things along those lines, where we have balanced cells and everything's under control. You could spend a full semester just talking about ANOVA designs and sort of partial invariants and things like that, and more elaborate types of methodologies. And traditionally, the idea with these is to pull the error term from like the 3x4 interaction, sort of that stuff, and use that to go through and calculate contrasts. The problem is that in the real world, we rarely meet the assumptions of those tests. And as soon as we start violating, our inferences are pretty sensitive to some of those types of things. And so while, yes, there are people who will say, yeah, you can do this, the sort of range of circumstances where that's probably a good idea are pretty narrow. And so my recommendation to you, and what will be easier probably to defend and easier to describe, is the approach that we've taken, where we go through and sort of split file if you get a between by within interaction, to split and then just look at within each one of those, sort of using that one-way repeated measures ANOVA to go through and run contrasts and things along those lines. Okay. Does that make sense? We can kind of see what the difference is with this stuff. Okay. All right. So this is going to be conclusions for the present example. We won't go through that because we haven't done that example yet, but use this as a reference. What we'll do is we're taking a look at how I might go through and tie all the stuff that we did for this into some sort of discussion summary, right? So we say operators, so we've gone through and talked about giving the interpretation of the interaction effect, right? Sort of talked about what that is. Make sure that you do that. If you find an interaction, tell me conceptually what that interaction means, right? Not that there's just an interaction effect, right? I want you to describe that. And so then when we got onto the follow-up test, we say a priori contrast used to compare self-reported willingness to maintain friendship with hypothetical combat survivors relative to aggregate ratings for motor vehicle accident, sexual assault, natural disaster, differences in willingness to maintain friendship and negative versus the combination of benevolent and personal. We're examined for each vignette in a series of exploratory analyses, talking about what we did. Modified TP procedure was used to control for the evaluation of post-hoc comparisons. See, that footnote is me, then sort of somewhere in the paper explaining exactly how we went about that, right? Because that was a lot of sort of ad-libbing stuff, right? So then we go a priori within group contrasts, offer compelling support for reductions in willingness to maintain friendship for hypothetical survivors of trauma versus other trauma groups across negative, benevolent, and interpersonal groups, right? So just summarizing, boom, 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 these were our statistics, right? So I can go down through and take a look at everything that we've got going on. Observed differences were greatest for participants in the negative profile. Data supported reductions in larger population ranging from 0.25 to 1.13 units. Corresponding within subjects affected indicated half standard deviation decrease in willing to maintain friendship to veterans versus other trauma groups for individuals in this profile, right? So I'm just talking about the magnitude of effect here. Participants in the benevolent and negative profiles also demonstrating reductions, reporting willingness to mainframe support, although within subjects, effects were modest with lower bound estimates corresponding. Christy, tell me what I've done with this paragraph here.
The middle one?
This one that I just said.
You discussed your a priori contrasts and split them up from the exploratory one.
Okay, yeah. So this is where, when we start to get into these analyses that are pretty complicated, right? You could run through and have a full-on paragraph for each one of these individual contrasts. Does anybody want to write that? Does anybody want to read that? Okay. So we start to get into a thing where we need to go through and summarize what are the take-home points, right? So what I've done here is I've said, well, my negative group is kind of the one that's got the biggest thing, right? So providing my statistics for all three of them, right? And saying that all three of these we found pretty strong compelling evidence against the null hypothesis, right? But then said, really, well, we've got greatest differences in the negative, right? Because that's really where I think sort of the story is talking about sort of interpreting my confidence bounds, right, for the point estimate of my contrast, and making an interpretation of my effect size, right? So you're sort of giving a sample for an example of the magnitude of what's going on there, and then saying benevolent and negative, the effects there were both probably pretty comparable, kind of rolling those together, say, yep, also found effects here, but it looks like the lower bound estimate, the confidence interval there, the lower bound for the actual population difference, 1/10 of a point, 5/100ths of a point. I'm not saying that they're not there, I'm just saying it's pretty minimal. Sort of really what's going on, it's the negative group that's stealing the show. Okay. People see how we kind of chime this together and do it in an efficient way that doesn't feel like, oh, I have to say the same thing over and over and over and over again with this stuff. Okay. So here we say exploratory analysis between subject contrast, indicating comparable range of willingness to maintain friendship in negative versus benevolent interpersonal profiles for accidents, sexual assault, natural disasters. So we didn't find much there. Didn't have strong evidence for differences. By contrast, willingness to maintain friendship with hypothetical survivors of combat trauma rated 7.75 is lower among participants in negative relative to benevolent. Right, so we're talking about the absolute difference here. Talking about magnitude. Observed differences exceeded conventional benchmarks for median effect, with data indicating 0.65 willingness to maintain friendship. So I'm just kind of talking about what I'm sort of cheating here and ignoring the two key facts. I think I can get into it down here. Results suggest both beliefs about the consequences of trauma, exposure, and type of exposure event, whereas individuals' evidence reductions in support for hypothetical survivors of combat versus non-combat trauma. Effects were particularly pronounced in respondents holding negative pejorative beliefs about the consequences of exposure. Similar data failed to provide evidence for differences in support ratings across negative versus combination of benevolent and interpersonal, except with respect to hypothetical combat survivors. Okay, so you see what I did there? I just did what I told you not to do and just ignored the whole Tukey situation with that. So I would, if I was rating my own response here, I would flag it back. What are you doing? Right? What this needs is something in there that says, yeah, we did see maybe some evidence that looks promising in terms of differences specifically for ratings of friendship for combat versus non-combat trauma. Sort of a difference in the negative group there, but this was exploratory and failed to meet a priori or sort of threshold for strong interpretation. So we're not going to pretend that it didn't happen, but there needs to be a statement in there somewhere that so we didn't technically meet benchmarks for interpretability. Therefore, those data should be considered preliminary and subject to further evaluation, something along those lines. Okay. See what I did? I just read you something that you could read for your own self, thinking that I was going to get there eventually, and I didn't. So, but it should be in there somewhere. Okay. Questions on sort of what I did. This is a lot. right? There's a lot of stuff that went on as we're trying to go through and tease some of these effects apart. Do people have questions about sort of how I kind of went through and constructed this? Does this help? Does this give people kind of an idea of, it seems like there's 1,000 different, we did a bunch of different stuff. How do I go through and talk about this all, right? Trying to give an example here. Questions? Okay. All right, so conceptual summary, repeated measures ANOVA, incredibly powerful designs, particularly for looking at within between subjects effects. What we can do is we can think about these mixed factor ANOVAs as having separate models. So we're looking at two different models. We've got a model that is looking at between subject stuff, and a model that's looking within subject stuff. Our between subjects model, that's different, just generally just pulling out individual differences stuff, but in some situations, those between group differences might be important, relevant, okay? Complications, we've got additional assumptions. We've got issues with calculating our omnibus effect size is gonna have you go through a Bateman article, talking about that generalized zeta squared, how we go through and do that. Then if we get an interaction, it's a lot of work to go through and say, how are we going to pull this apart? As you're going through, if you find interactions, things that you need to do before on the front end. I'm going to give you a game plan for this assignment. I'm just not going to turn you loose because I get 1,000 different approaches, and that would be too much for me to try and figure out. But a priori hypotheses, before you go through and put this together, one thing, should I have mixed factors ANOVA with 7 different factors in it? No. Because God help you if you find like 4-way interaction within and between and stuff, it's going to be a mess, right? So warning that you not bite off more than you can chew, but before you start, having an understanding, okay, what's the most important stuff? What do I expect to come out of this? Lay those a priori hypotheses down in the first place, and that's going to get you a huge head start. So making sure you got a priori hypotheses, thinking about the nature of the data, right? Do we have ordered effects, or do we have things that are sort of interchangeable? Do we need to, based on the omnibus effects that I have, do I need to have accommodate, can I get this within subjects contrast, between subjects contrast? Do I need a little bit of both, right? Really, I could have reasonably qualified that interaction that we saw with just the within subjects effects. That would be probably an okay way to go through and do things. But then there was some between subject stuff that might also be interesting, just given on the pattern of means. And so thinking about, do I need to go within, between, some combination of the two? How many comparisons am I going to run? And then consequences of unequal cells, violations of homogeneity, variance, these types of things. Okay? And this is really starts to become important when I'm deciding which contrast effects to interpret. How do I deal with effect sizes? And am I able to go old school and just pull that error term out of the within subjects effects from my overall ANOVA, from the overall sort of factorial ANOVA, and use that as the error term for my contrast? Probably not. Not saying never. If you do that, there's sort of, you get the benefit of capitalizing on aspects of the design, sort of increased degrees of freedom and things like that. But there's a huge concern with if you have violations, that starts to degrade your confidence that you can make reasonable inferences from those contrasts and tests. And so probably your safest bet is to just fall back on, if you're looking at within subjects in an interaction, looking at one way to repeat measures and repeat measure ANOVAs at each level, and then sort of doing between subject stuff. All right, questions? How are we feeling about repeated measures designs? Good. Anybody in the process of developing a thesis that might use repeated measures or mixed factor ANOVA? Okay, that's all right. By not next Friday, the Friday after that, you guys will all be masters at this stuff, so you'll just be cranking them out for fun. So, all right, cool. 3:30, like, bam, dead center, right in the middle. So I'm good, right? Sometimes I impress even myself. Let's go through, take a break, and we'll jump into regression stuff when we get back. I like the directing.
Yeah, director, yes.
And
I always wanted to act, but directing is fine.
Yeah,
He's boss.
let's stick to behind the camera, Chris.
All right. So, going to make a transition into regression stuff. Question, and I've asked people individually, who has exposure to regression, background in regression, taking classes in regression, do anything with you guys? Like folks, okay, cool. So approach to the stuff that we're going to be doing in terms of regression stuff, going to be same in terms of interpreting, in terms of like hypothesis testing. Again, any inference test is basically just asking whether or not some value or some population coefficient is equivalent to 0. We're just going to go through and sort of talk about things in terms of continuous sense, and then we're going to get some partial coefficients and things. This used to be one mega lecture. It's still kind of busy, just breaking slides up into different sections. Today we're just going to go through, get through the basics, talking about model selection, when we might use regression, what types of questions we might answer within the social sciences. Talk about bivariate regression. That's going to be models that just contain one individual predictor and one outcome. We get a multiple regression and finish up with different estimators that we can might use. Okay. So, from a classic perspective, from the development, in the original development of regression, the idea here is to predict scores on some continuous outcome with a regression model. The idea is that I have some outcome of interest, and what I want to do, so the original conceptualization of regression was to systematically collect information that might predict some continuous outcome. Okay? We're talking about bivariate regression. We've got one single independent variable, right? And again, talk about this as there's no real good way to talk about this, right? If I talk about independent variables and dependent variables, sometimes people who are very, very strong from experimental tradition will be like, well, they're not independent variables because you didn't manipulate them, so on and so forth. And dependent variables, it's an association, and so it can go either way. Regression, it actually doesn't, because things sort of fit together different. But sometimes people will call these predictors, but then if you're a social scientist, you get upset because if things are measured concurrently, you're saying, well, that's not a predictive relationship, and that it's predicting something in the future. But I can predict something happening right now. You'll see different people talking about this in different ways. I'm not going to get too upset in terms of how we're talking about this, but you may run into people at some point in your career who get really worked up about sort of the names that we give. Sometimes people will talk about predictors or IVs as covariates, which just means so they're just a group of variables. So the nomenclature differs a bit. I really don't think it matters a whole lot as long as you know what you're talking about and sort of know what you're doing and stuff. But in the bivariate regression case, we've got one single IV. And this predictor can be either continuous or dichotomous, okay? So if we have a continuous predictor, that's fine. Or we can have a categorical predictor that's 0, 1. That works too. But as soon as we get into categorical variables or ordinal variables where we've got 1, 2, 3, where they're sort of categorically different things, we have to do some differences in coding to go through and address those. We can do it. Regression is incredibly flexible. We just need to be careful and sort of not taking, let's say, some nominal variable, like a condition variable that we've labeled 0, 1, 2, 3, and then just using that as a continuous predictor, right? So our inputs need to be continuous or dichotomous, one continuous outcome. Bivariate regression, your standardized coefficient is going to be the same thing as Pearson correlation, no different, right? The only thing that we get with a regression analyses is an actual regression model where we can actually plug values in and start to predict some outcome. When my independent variable is dichotomous, it's equivalent to a t-test. Okay? Everything that we did last semester with our means-based tests, in terms of ANOVAs, in terms of t-tests, things along those lines, you can all run that as a regression if you with proper coding. It's functionally equivalent, right? The nice thing about regression is it ends up being a little bit more flexible in how we deal with stuff. Okay, so that's our bivariate regression. Multiple regression. Here we have multiple independent variables, some combination of continuous dichotomous predictors and one continuous outcome. Here equivalent to ANOVA and COVA, as long as we properly code things and create interactions and things along those lines. Okay. So what research questions? One might want to use a regression model. Again, classically, what we're trying to do is predict some outcome. But what we've done within the social sciences is adapted this to start looking at different questions that aren't necessarily sort of prediction sort of down the road in a classic sense. One thing that we might want to ask, and this isn't something that happens a lot in psychological science, but we could ask it, is how well did our regression model predict some outcome in our Y, right? This is more of a classic question in regression. I've got, for marketing or business type of area, I want to have some functional outcome, and I want to say, how can I best predict this thing that's happening down in the future? What I might have is a regression model that goes through and makes an attempt with a number of different variables to predict some outcome down the road. And my question might be, how well does this model predict my outcome? What we're going to do is we're going to test this with our R-squared value, right? Our R-squared value in our regression model tells us the proportion of variability in our outcome that's accounted for by sort of the predictors that we have in the model, okay? So this is our R-squared. This is a big, small as rho. What's that?
Roll.
Is that rho?
Yeah, that's rho.
Okay. So our null hypothesis here is the population R squared is 0. Like that, our null hypothesis is that, in actual fact, population coefficient for R squared is equal to 0. Like our combination of predictors account for 0 variability on the outcome. Okay. We can also ask, what's the unique association of our variable x with outcome y controlling for other variables in the model? Okay. We're going to get into this in terms of thinking about, once we account for shared variability with other stuff, what's the unique association of this predictor with my outcome variable? Okay. If my predictor doesn't share a lot of overlap with my other predictors, that might be a large value. If it's hugely overlapped with a bunch of other stuff, maybe not so much, right? What we're going to do is we're going to look at individual coefficients for this. And again, our null hypothesis is that the population coefficient is equal to 0 in that my predictor has no association with the outcome after I account for other things in the model. Okay. Last question, we might ask about what's the incremental contribution of variable x or set of variables x in the prediction of our outcome above and beyond stuff we've already included in the model. This is going to be a question that we're going to look at R-squared change here, right? So I've got, give me an outcome, something that's relevant to you. What are you interested in? ADHD, okay. ADHD impairment on a sort of 0 to 100 scale, right? And what are things that we know predict impairment in ADHD?
Sleep.
Okay. Sleep?
Number of symptoms.
Okay, severity. What else? Age. Okay, so let's say we've got in the prediction of severity of ADHD, we've got let's say sleep hygiene, some measure of that, right? Severity of symptoms and age, right? And so we know that these things count for some proportion of variability in functioning. But then I've got to go other couple things. Maybe I say I've got a measure of executive functioning and family history of ADHD or symptoms or something like that, right? My question might be, does the combination of those two other variables, do those add to the prediction of functional impairment above and beyond what those other three are, right? And if I add those two variables to the model, how much does my R-squared change? How much of the total piece of the pie is changed with you generally sort of know account for some proportion of variability in the outcome? Well, what if I add these other two things? Does that help us in the prediction and account for variability in my outcome? Then I might ask, so is there a change in is that incremental increase in the prediction of variability in my outcome, is that some positive number? Okay. So a lot of different things we can ask, depending on what our research question is. We're going to focus on individual. For psychological science, number 2 is probably the thing we generally use regression mostly for, but any of these are fair game. Okay. Questions? All right. So, example of just conceptually what's going on with our regression models. So let's say I have a group of students out in the hall, okay, group of undergraduates out in the hall, 100 people out in the hallway, okay? And I know that the average weight of the students out in the hallway is 150 pounds, okay? There's some way I just know that that's what it is, okay? I go through and I randomly select, or I have Siley go up, Alicia, Siley goes out and randomly selects one student out of that group, and I don't see him. Siley's out there, she's like, all right, I got this student by the scruff of the neck. And she says, Siley's grab people like that. And she says, statistically, what's my best weight for any given individual in that sample? What's my best guess? I don't see the person, I just know that Siley has someone captured out there out of that sample of 100 students. What's my best guess for the weight of that student?
Around 150.
What's that?
Around 100.
Around 150?
What?
150.
150. That is my best guess, right? Am I going to be right?
No.
No. But I'm going to be the least amount wrong over repetitions if my answer every time is 150 pounds, okay? That's just guessing the mean. In the absence of any information, my best guess in terms of the average student, average weight of any single student is just to guess the average, just to guess the mean. I know I'm going to be wrong, but I'm going to be less wrong than if I were to guess anything else, okay? What if, however, okay, Sally goes grabs a different student. She's like, all right, I want you to tell me, take a guess at how much this student weighs. But I'm going to tell you how much how many credit hours this student is taking, okay? Alicia, what's my best, so I know, so that this student is taking 15 credit hours. What's, and I have to guess their weight. What's my best guess statistically?
150.
Why is it 150? I've got new information, right? I know how many credit hours this person is taking.
But we don't know how that relates to the weight.
Do we expect it to relate to weight?
No.
Probably not. I don't know, maybe, right? I could probably come up with some type of a sort of scenario, but probably not, right? I have information that has systematically no association with that person's weight, and so I can take that into consideration, but I'm still probably going to say 150 pounds because I don't expect number of credit hours to have anything to do with anybody's randomly selected weight, okay? All right, Cider captures one more person, right? Got him. And says, hey, once you get the weight of this randomly selected person, but I'm going to guess, I'm going to give you the student's height. This person is 6'2". What's my best guess in terms of that person's weight?
Still 150.
Is it? Do I expect the average person in that hallway to be 6'2"? No. What do I expect? Is that person taller or shorter than the average person in the hallway?
Probably taller.
Okay. So what is that going to do? Is there going to be any adjustment to my guess of their weight? Probably. And so what might your guess be?
Definitely more.
More, right? What if I say, oh, this person is 5'1"? What's going to be, is that going to make any difference on your guess? Yeah, probably lower, right? And so what we have now is information that starts to make a systematic adjustment on my prediction of weight above and beyond just guessing the mean. In the absence of useful information, right, my best guess is just the mean every single time. But as soon as I have additional information that starts to systematically change above and beyond, right, then I can start making adjustments in my best guess that go above and beyond the mean. And this is what we want to do. We want, with our regression models, we want to have variables in there that help us make adjustments above and over and above the mean, right? Does this help me? Is this information that helps me make an adjustment to guessing the mean, right? So we can think about mean is where we start, and then start making added adjustments up or down based on the value of variables that we have predictors in the model. Okay, we'll kind of see the idea. So we'll start with mean. That's our best guess, but then we're going to go through and make adjustments. So the goal of our regression, bivariate regression, is to summarize our association between x and y using basic linear model. Okay, this is our regression models are probably our most straightforward application of generalized linear model. So it's in its basic form. We were looking at a basic regression equation here. And that equation is going to define some straight line that characterizes the association of x and y. Okay? So here we have height, and here we have weight. Here's our small sample. What we're looking to do is we're looking to find the line that best captures the linear association of height and weight in this set. Okay? And so here's my regression model. Okay, this is sort of we argue this is the most simple form of the generalized linear model. Okay, so we got y hat for person I equals a plus bx for person I plus e for person I. Okay, our y hat, this is our predicted score. This is our expected value of our outcome. This is our predicted score. Okay, Sean, is this our real score?
No.
No, why not?
There's an error term.
Because there's going to be an error term. Based on my model, right? Based on the information I know, this would be my best guess for Ignacio's weight, right? Do I think I'm going to be spot on with that? Probably not. I know I'm going to be off by probably a little bit, right? Unless I hit the jackpot and just happen to, Ignacio falls directly on that regression line. But this is my expected value. Based on my model, this is my predicted value for that individual, okay? A, this is going to be my intercept, or my regression constant. This is going to be the value of my predicted value when x is equal to 0. Nick, can you tell me why this is true? Yeah, why math?
If it was 0, then
Yeah, if I plug 0 in for x, that goes away. All I'm left with is my intercept there, right? So when my predictor is equal to 0, my intercept is just the expected value of my outcome. Okay. This error term, we'll get to that in a moment. We're assuming that that is on average equal to 0, right? So if I plug 0 into there, everything goes away. I'm just left with this. Okay. So if we think about this, the credit example, right? Does credit hours have any systematic association with someone's weight? Probably not, right? So if this is 0 anyway, and I plug 0 in, and so that all goes away, and I'm just left with me, right? My best guess. What we're seeing here is an adjustment up or down based on my predictor. But what I'm looking at is when everything is equal to 0, my constant here is just giving me my expected value of outcome when everything else is held equal to 0. This is an incredibly, incredibly important concept. Keep this in your mind, right? If I plug 0 in for my predictors, this is just the expected value of my outcome. Okay. B, this is my slope or regression coefficient. This is giving me the change in my expected value, the expected value of my y given a unit change in x. Okay. So CJ, if my b is 2, right, and I say, let's say b is 5, and I'm predicting weight based on height, right? And I'm measuring height in inches. If I sort of add 1 inch of height to someone, how much do I expect their weight to change by?
5 pounds.
5 pounds, right? For every unit increase in my predictor, this is the expected change in my outcome. TJ, does that mean for every inch that I add to some person, they will 100% always be 5 pounds heavier?
Nope.
Nope, it doesn't. But that's what my model's predicting. On average, with every increase in height, 1 inch unit increase in height, I'm expecting a 5 pound increase in weight or something like that, okay? And my X, this is my observed value of my predictor for case whoever that individual is, and then E is my residual, okay? Our residual, almost for the types of regression that we'll use, my residual here is defined by the difference between my actual value and my predicted value, right? So I predict that Chris is going to have this score on a measure of extroversion, right? My model predicts that Chris individually, based on whatever prediction, whatever variable I have in there, that his score will be this. The difference between what I predict Chris's score to be and what Chris's score actually is, that's my error term. This is my residual, okay? And you'll see that I have an asterisk here. Sean, why do I have an asterisk on this as the residual?
I'm guessing because normally it's against the average of Y. It's the observed minus the average of Y.
That's a different part of it. No, that's not your error term. This is if we're using OLS regression. This depends on our estimator, right? For our ordinary least squares regression, when we talk about estimators, for the types of, in social sciences, the types of regression that we do, this is our error term, this is our residual. If we use different types of regression, this changes a little bit, but for the types of stuff that we do, this will almost always be our residual right here. Okay. So questions? Tomorrow, what does my intercept represent?
The actual score when X is 0.
Okay, not the actual score, my predicted score. My predicted score when my variable or variables are held constant at 0. Okay. Sally, what does B tell me?
The slope.
The slope, right? Based on my model, the expected change in my outcome given the change in my predictor. Okay. So these are fundamental things, like important to have a good understanding of this conceptually. Is as soon as we switch over and start talking about moderation and having to work with these models, you'll be happy that you've done this. Okay. Questions about this? All right. So, ordinary least squares. Most common estimator that we see, at least in psychological science, is going to be our OLS estimator. And what our OLS estimator is trying to do is we're trying to use this as a means to identify and calculate values for my intercept and my slope based on the deviation between my observed outcome and my predicted outcome, okay? And so what I want to do with ordinary least squares is I want to minimize the sum of the squared residuals for all of my data in the sample. So what I want to do is I want to select values for my intercept and my slope that minimizes the distance of any individual data point from the predicted value for that person. Okay. So here I've got some actual data where I've got for my Psych 1000 class, I've got quiz 1 scores and scores on the midterm. Okay. Sally, what type of association am I seeing here?
Predictive?
Yeah, actually, yeah, this is a good predict because quiz 1 happened sometime here and midterm happened there. So it's a predictive relation. How else would we qualify this? Chris?
It's a positive association.
Positive association. What do you mean by positive association? What does that mean?
As midterm scores, or as quiz 1 scores are higher, so our midterm score is higher.
Exactly. Honestly, I could actually predict people's grade. Like after day 3, when they take quiz 1, I've got a good idea of where they're going to end up sort of by the end of the semester. Like it's crazy, like how sort of stressing how predictive this is, but it is very, very strong, right? And so it's a positive association. As people do better on quiz 1, Alicia, how do I expect them to do, or how do they actually really tend to do on the midterm? Better, right? As people do poorer, the outcome looks grimmer in terms of the midterm, right? Well, what I might want to do is not just say, oh, there's a positive association. I might want to go down through and actually try and predict how people are actually going to do and come up with an individual score for individual students, right? And so what I would do is I could run this in a bivariate regression. And if I do this, here's my regression model, and this is what I get, okay? I get my expected value on the midterm is equal to 23.96 plus 0.60, okay? So, Ignacio, tell me, so give me an interpretation of this regression coefficient here.
So if you get a 0 in the quiz.
Oh, it's not my regression coefficient, my 0.6 here.
You only is the rate of change. So if you increase quiz by 1 point, midterm will increase by 0.6.
Right. So this is not perfect, but my model suggests that for every unit increase, for every point increase on quiz 1, I'm expecting a little over a half a point increase on the midterm. Right? Nick, what about my intercept here? What's my interpretation here?
If your given value, your x 0, that's what would be left over for your predicted value.
Okay. Yep. Let's put this into the words, into sort of the variables that we're actually looking at. So what does this literally mean?
If someone scored 0 on quiz 1,
Yeah.
then they would get a 23.96.
Okay. If someone were to score a literal 0 on quiz 1, I would expect based on this model, I would expect their midterm score to be a 24. Okay. Does this make sense? Yeah. Kind of. What's the hang up with this?
Your data doesn't include that value.
Data doesn't include that. Yeah, and so I should clarify. This is a 40. Quiz 1 is a 40 item multiple choice question or multiple choice quiz.
The 23.96, the intercept term, is a result of the aggregate of all the responses that you have.
So it's a result of and so it's my best predicted value if someone were to get a 0. Does anybody get 0 on a 40-point multiple choice quiz?
Some people come close.
If someone actually actually completed this and actually got a 0, I would accuse them of throwing it, right? Like, in the absence of any information at random responding, what should you get? 25, right? Like, if you get a 0, that means you knew all the answers and intentionally selected the wrong one. This is what you use in sort of malingering stuff and sort of other areas, right? Is 0 a real score for something that actually happens on the midterm? And people actually sit down and take it, or on quiz 1? No, it's not a real score, right? And so what we're going to talk about with this, so yes, literally, if someone were to score a 0 on quiz 1, I would expect their midterm to be a 24, right? But that's falling outside. Here's my data. Like, that's happening down. No one exists in that spot, right? And so what we start to do is we start to get into these models is when we get down the road, we'll start talking about how do we go through and maybe make that 0 point something that means something as opposed to a literal 0 on the scale. Similarly, if this was the regression of height onto weight, right? What would that intercept mean? I mean, for someone who weighs 0 or someone who is 0 inches tall, this would be the expected weight. Anybody 0 inches tall? No, it's not a real thing, right? So thinking about this starts to become very, very important when we're working with our regression models. What does 0 mean, and is it interpretable, reasonable? Okay, tuck that away. Yeah.
practically speaking, is it a coincidence that your intercept term is close to 1? Do you do like A, B, C, D options? So is it like coincidental that that's 1/4 or 25%?
Oh,
Yeah, it is close to random,
Yeah.
random selection.
yeah, no, I think that's coincident. I hadn't,
Okay.
that's smart, I hadn't thought about that, yeah. So in the absence, if someone were to literally get a 0, I would expect them to improve. Go through, had a really, sort of, basically they're scoring a chance at about 25%. And anytime I see that, if someone's literally scoring a chance, I have 3 different versions of the test. I'm worried that they maybe got scored it with the wrong key, right? And so I went through and sort of followed up and saw, oh, this person actually, we scored it with the wrong key, right? So basically, their exam scored at random. I was like, okay, well, that's why they got 25 is because it scored it at random. So we went through, rescored it with the right key. Guess what their score was? Exact same thing. I gave them an A in class. It was so impressive in an effort. Like when we scored your exam with a random key, and it was the exact same scores you would have gotten if you scored the right key. It was just pretty. I was impressed with the effort there, but that's neither here nor there. It has to do with progression. But people seeing what's going on with this stuff. Okay, so what we've done here is we've selected values for the intercept and for the slope that minimize the difference between minimize the error between any actual value and the predicted value, okay? So for example, I've got someone here and someone here, right? This line minimizes the distance between their actual score and their predicted score for everybody in the set. Okay? There is no other line that I could draw through this cloud of points that would do a better job of minimizing the difference, the deviation of everybody's individual score from their predicted value. Okay? But let's say if, I don't believe that's true. I might, screw you, OLS regression, I got a better regression line, right? And what I'm going to do is I think this intercept is way out, right? If someone literally scored a 0 on quiz 1, I don't think their score on the midterm would be that high. I think it would be much lower, right? So I'm going to go through and I'm going to say the intercept is actually 3.69, right? And so if I do, and I draw that line, now all of a sudden these 2 points have gotten a lot farther away than they were before. Everything is a lot worse off. The sum of my squared residuals is much, much larger than it was where I had it before. So I say, okay, well maybe actually we'll go a little bit higher, right? So we move it up, change the intercept to 38.96, right? Again, we're still worse off than we were before in minimizing the distance between everybody's actual score and their predicted score based on my model, okay? So I say, okay, fair enough, whatever, right? Intercept's fine. I'll accept intercept at 23.96, but I think this slope is off, right? I think really the slope probably ought to be 0.7. I think sort of there's a stronger association there. So I draw a line here, and I get closer at this person, right? Before, oops, right? I get closer to this dot, but now this one's way farther off. So I sort of, in adjusting to better fit this piece, I've gone through and made the fit of the rest of the model worse, right? Same thing if I make it slope less, I've gotten closer to this one, I've reduced the residual there, but I've massively increased the residual for this, right? And so what we find with OLS, by definition, this line, this regression equation, the values that we select for my intercept or my slope, the whole function of how this works is it's minimized the difference between my predicted values and my actual observed values for everybody in the set. If we're using OLS regression, there's no values for these that would decrease the error in my prediction based on the data that I have. Okay? People understand kind of what we're doing, how this residual works here? Okay. So what we're trying to do here from a mathematical standpoint is we're trying to minimize the squared residuals. This is our loss function. Okay. So we want to, from a mathematical sense, we want to minimize the sum of the squared deviations from my actual value minus my predicted value. Okay? And if I take my predicted value and substitute. I know that my predicted value, right, my regression line, right? So if I know what I'm trying to do is I'm trying to minimize the squared deviations between of y, my actual value, and my predicted value y hat. Well, I know that y hat is equal to a plus bx. I just substitute a plus bx in here. This ends up as my loss function, okay? And what I want to do mathematically, simultaneously solving for a and b is going to give me equations that give me the minimum possible residual value for these data, right? So if this is, if I'm looking at my slope, this is the sum of my squared residuals, and this is the value of my slope. If my slope is too low, my residuals are high, and as my slope gets higher and higher and higher, I get to a point where it hits its minimum. My squared residuals are its lower point. If I make the slope start to increase beyond that point, my residuals get higher and higher and higher and more. So what we're doing is we're trying to find this minimum point that minimizes this association right here, okay? And so what ends up happening is to solve for this, we find that my regression coefficient is equal to the covariance of x and y. Chris M., remind me what covariance is.
The degree to which one variable changes with the change of another variable.
Right. It's basically the variance version of the correlation, right? So it's just the covariance of x and y over the squared standard deviation of x, or the variance of x, gives me my regression coefficient. And then once I have my regression coefficient, my intercept is just the mean of y, the mean of my outcome, minus, there we go.
Is it working?
Take two. All right. So what we see with this is that my optimal values for my intercept and my slope are going to be directly related to the mean variance and covariances of x and y. Okay. So with our bivariate regression, and this is where when we talk about regression being a means-based analysis, right? Because everything's deviating from that mean value, working with variance covariance. Yeah. Okay. People in general see kind of what is going on with this regression model and how we're trying to go through and sort of at least conceptually what the goal is with this. Okay. All right. So when we're running an OLS regression, some basic properties. Okay. These are things that are true by definition. The sum of my residuals, the sum of my individual errors for my participants is going to be equal to 0. If I go through and I added up all the errors, my sum is going to be 0. Okay. The sum of my squared residuals is the minimum possible value, because we talked with our loss function. The sum of my observed y's is equal to the sum of the predicted y's. So if I took everybody's outcome, score on the outcome variable, and I added up their predicted score on the outcome variable, they would be identical to one another. Okay. Sum of the products of my x values and my errors is going to be equal to 0. So if I took people's predictor times their error, multiplied those, and add those up for everybody, you're going to get 0. Sum of the products of the predicted y and my errors is equal to 0. And my regression line, by default, by definition, is going to pass through the point mean of x, mean of y. My regression line, so the mean of x, the mean of y, wherever that intersection is, my regression line will always pass through that point. So, how do we go through and start to partition variability out of sort of this analysis? Our goal for our regression model is to maximally predict variability in my outcome, whatever y is, okay? And when we're talking about variability, we can talk about sums of squares, right? Sum of squares is just a measure of variability, same thing as variance, same thing as standard deviation. It's just a raw metric of the degree to extent to which things differ and jump around, okay? So the degree to which we can make a valid prediction of individual outcomes, this is the standard for determining whether or not we have a good regression model or not, right? How well are we able to predict the outcome that is sort of on the back end of our equation here, okay? So without valid predictors, if I have nothing in there that predicts any variability in my outcome, mean is my best guess, right? I got 100 students out there and you give me eye color, I don't know. I guess I'm just gonna guess the mean. That's my best guess in the absence of any reasonable thing that has anything to do with the outcome, right? And so this discrepancy between everybody's actual value of y and the sample mean, this is the total variability, what we'd like to account for. So Sean, when we're thinking about the difference between people's actual score and the mean of the sample, that's all the variability in the outcome that we're trying to predict with our regression model. Okay. We can also think about this as total variance in the set, right? If I just went through and calculated the sum of squares for everybody in the set, this would be my sum of squares y. This is all the variability in my outcome, right? This is anybody's deviation from the mean. This is what we're trying to account for. So what we can do is we can take this total variability. Think about sum of squares y. Sum of squares y is the total piece of the pie. This is everything that there is to account for. Okay? What we can do is we can break this into two different pieces. We can take a look at the difference in the mean of y from the predicted score. Okay? So we can take y hat minus the mean of y. This is giving us a measure of the extent to which we're able to make a unique prediction for every case. Okay? So to the extent that here's my regression model, and it actually predicts something in my outcome. Here's my predicted value. Here's the mean of everybody in the sample. That deviation there, this is going to be the extent to which I'm able to make a reasonable prediction, right? Because if you give me eye color and I'm trying to predict weight, what's my best guess for everybody? The mean, right? And so if my predicted value is the mean, and minus the actual mean, then 0. My model has 0 predicted value. I'm not able to predict anything, right? But if you give me height, right? Now all of a sudden I can make an adjustment on that, right? That differs from the mean, and this is going to give me, this is telling me, this is going to be the sum of squares regression. This is going to give me the extent to which I can predict stuff. Okay? I can also split this into the difference of the observed y from the predicted score. This is going to be my residual, right? This is the difference between what I predicted and what their actual value is, okay? And this is going to give me an index of the accuracy of scores. So if my predicted score is actually really, really close to their actual real observed score, what does this tell me about my model? Ignacio?
Again, please, can you answer?
Yeah, so if my predicted score is actually really close to the observed score, what does that tell me about
The
the model?
variability is
Yeah.
very.
I've got a pretty good model, right? I'm pretty good at predicting, right? If my predicted value is way off from everybody's actual value, I don't have a great model, right? So this residual is telling me the accuracy of my predicted scores. Okay. So total variation in y, all the variability in y. So the difference between individual scores, the sum of the squared deviation scores from everybody's individual value minus the sample mean. Total variation y is going to be equal to the difference between the predicted value, the squared deviation of the predicted value minus the mean, plus the sum of the actual value minus the predicted, sum of that squared deviation score, okay? Which is going to break us into different sums of squares. So my total sum of squares, my sum of square of y, this is the total variability in y, okay? This is the sum of the squared deviations of everybody's actual observed score from the sample mean, right? This is just variance. This is just sum of squares. This is not different than any other variance estimate. This is just all the variability in y. This is what we're trying to account for. Okay? Our sum of squares regression. This is represented as the deviation of the predicted score from the mean score, right? How much is our model able to predict above and beyond the mean? If you give me garbage nonsense predictors, and essentially I'm predicting the mean for everybody, then my regression has no predictive value. Yeah, I'm guessing the mean, right? No matter how many variables I have. But if you give me reasonable variables that hold unique association with my outcome, then my predicted value is going to be different than the mean, and so this is going to give me my sum of squares regression. Sum of squares residual, this is how wrong we are, right? So here's my predicted value, right? This is my predicted value for tomorrow. I say tomorrow has a score of 50, right? Turns out tomorrow actually has a score of 45, right? That's my residual. How much I was wrong, how much I was off for tomorrow. and for every person in the set. That's my residual, that's my error term. So my sum of squares y is going to be equal to my sum of squares of residual plus my sum of squares of regression, right? And so my total variation in y is the sum of my predicted variation plus my residual. People following along, kind of seeing how this is broken out. Right? So if I want to then look at the proportion of the total variability predicted in my outcome, I can take the sum of squares for regression, which is my prediction above and beyond the mean, over total variability of my mean. This is going to give me my R-squared value. This is the total proportion of variability or percentage of variability in my outcome that is accounted for by my predictive model. And do we want large R squared or small R squared? Large R squared, right? We want our model to do a better job of predicting outcomes. Right. Conceptually, how are people feeling with this? Kind of getting it? All right. Also, for our bivariate regression, where we just have one predictor and one outcome, R squared is the same thing as squared correlation. It's one and the same. Okay. Makes sense? Yeah. All right. R squared, so we tend to think about R squared as a proportion of variability accounted for by our model, or in our outcome accounted for by our model. We can also interpret R squared as the proportional reduction in error variability due to knowing the predictors, right? If I know nothing and have no predictors, here's all the variability. With the predictors, how much does that reduce sort of the error into whatever it is I'm trying to predict, right? So if I have good things, it sort of increases predictability. Think about this as predicting variability or reducing error. So it's just a different way to think about it. So, anybody, as I was talking about proportion and variability, any ANOVA stuff popping up in people's minds as they were thinking about stuff? No? That's fine. We talked about this, proportion and variability in terms of ANOVA. Regression, ANOVA is just a special case of regression. It's no different, okay? If we want to think about this in terms of visually here, right? My sum of squares y. Again, this is the total variability in y. So here I have a number of data points. Here's the mean of y. This red line is the mean of y. Total variability is the sum of the squared deviations of everybody's score from y. Okay? This is just all the variability in my outcome. Okay? So this is the total variability. This is what I'm trying to account for. Okay? My sum of squared regression, this is the sum of the squared deviation of my predicted value relative to the mean. This is how much my model does in predicting outcomes above and beyond just guessing the mean. So for all of these individual dots, right, we've got so the difference between the predicted value and my outcome. Okay, so here we've got a low point, right? How much better is my regression model at predicting this score than just guessing the mean? Alicia? Pretty good, right? So here's the outcome, and this is what the square box is what my model predicts. Here's the mean. So my regression model did a really nice job of predicting sort of that above and beyond just guessing the mean, right? But then we've got a case here where here's my value, but here's my predicted value. Did my regression model do much in helping me predict that case? No, that's actually pretty bad. Like I'm pretty way off, right? For that individual case, I probably would have been better just predicting the mean, right? But as I go through and I take a look, sort of in general, I've got through these data a pretty sort of strong predict. My regression model, the expected value deviates quite a bit from just guessing the mean, and so this is going to be my sum of squares regression. How much my model does in terms of accounting for stuff above and beyond just predicting the mean value for everybody. Okay? This is the predictive quality of my model. Okay, and we got our sum of squares residual. Sum of squares residual is just the sum of the square deviations of my actual observed y relative to my predicted value. So here, residual's pretty small. Did pretty good here. Massive residual right there. That's what I was way off in terms of predicting that. Also not so good at predicting this one, right? But in general, my residuals look to be better on the high end than the small end on average, but so whatever. Okay. So sum of squares regression, this is analogous to our sum of squares between in our ANOVA, right? Remember, our sum of squares between was captured by how much our group mean differs from the grand mean, right? What you can do, if you think about regression as an ANOVA with an infinite number of groups, that's basically what a regression is, right? So now this is kind of a simplified example, but if we had lots and lots of people, right? There's probably going to be a lot of people at this x, right? Right? And so this is just going to be what we're looking at is how much do we deviate from the mean value of everybody here. So think about your x in a regression model as a continuous measure. Same thing if we had an ANOVA and we just had treated every individual score on x as its own group. Okay? So our sum of squares regression analogous to our sum of squares between how much how much difference do we see from the mean value of everybody at this level of x and everybody at this level of x and everybody at this level of x from the grand mean. Okay? Our sum of squares residual is analogous to our sum of squares within, right? So for everybody with this value of x, how much are they deviating, or excuse me, how much are they deviating from my predicted value? And what we get is a significant model identified by the ratio predicted to variability, total variability, taking my sum squares regression, divided by my sum squares total, and this is going to give me my R squared value. So this is important, and it's going to be, as we start to think about working up towards more complicated types of regression and some more in-depth analyses, wanting to be very clear on what your sum squares, why is sum squares regression, your sum squares residual, right? We've got here total variability in my outcome. Here we've got the deviation between my predicted value and the mean. Here, the deviation between my predicted value and my actual value. Okay, Chris?
So if it's analogous to ANOVA, can you convert your R squared to F?
Not to an F. What can I within ANOVA, what can I compare? What's the analog of R squared?
I don't remember. That's why I asked.
Someone help him? What was our effect size for ANOVA?
Oh, eta?
Eta squared.
Yep.
Eta squared, right? So eta squared, if I in my one-way ANOVA, right, my eta squared is just telling me my eta squared is telling me how much variability in my outcome is accounted for by my predictor variable, right? It's a measure of association. It's identical to R squared. When you're running ANOVA and stata, it gives you an R squared. That's your stata, or that's your eta squared. So exactly the same thing. Other questions? Okay. So significance testing. This is basic output from SPSS. When we run just a simple regression, regressing y onto x, that's another thing too when we're talking about regression. We always regress the outcome onto the predictors. It's kind of backwards with the way you might think about it. We're always regressing y onto predictors x. And if I have one variable, predicting y onto x, I'll get a model summary here. Here is my R squared value, right? So in this case, we've got 24 cases labeled x1 and y, and it looks like my R squared for this regression of x onto y is 0.605. CJ, what does this mean?
Zero.
Okay. So this is my R squared.
Is that just as your x? No.
How would we interpret this variable?
Proportional
The model predicts 60% of the
Okay,
variance.
so the model predicts approximately a little over 60% of the variability in my outcome. And when I say the model predicts, what am I talking about in this case of bivariate regression?
The X.
What X predicts, right? So basically what this is saying is that my predictor X accounts for a little over 60% of the total variability in my outcome. Okay, in a bivariate case, easy. In general, your R-squared is just, this is the proportion of variability in your outcome that the model is predicting. But in this case, my model includes one variable, so there we go. Right? Also, as we move down here, right, we see we get an ANOVA table. We get our sum of squares. These are the sum of squares that we just talked about, right? Sum of squares regression. Right? This is the sum of the squared deviations of predicted values for every person, every individual in the case, as compared to the average of my outcome. Okay? This is how much we're predicting. Sum of squares residual. This is the sum of the squared deviations of everybody's individual predicted score from their actual score. And then the sum of squares total, this is my total variability in Y. So if I just took Y and calculated the sum of squares of Y, that's going to be right there, right? I can take that, I can turn that into a variance estimate, and that would just be the variance of Y. Take the square root of that, turn that into standard deviation of Y. That's all that is. That's just variability in my outcome. Okay. We'll also see that we have an F-test. In my overall ANOVA, you have an F-test for, yeah.
How'd you get the F-test?
What's that?
I was wondering how you were going to get an F out of this.
Right? Well, you see, here we go. We got sum of squares, degrees of freedom, mean square, residual, degrees of freedom, mean square. There we go, right? Got our mean square divided by our mean square regression divided by our mean square residual. Okay? So this is just the same ANOVA table that we worked with last semester. We're just using this in terms of regression. Yes.
Can you use like the weird W thing for X? I can't remember what it's called right
Omega?
now.
Omega?
Omega.
Okay.
For like effect size for this, or would you want to use eta or not eta R?
Yeah. So this is a good. Hold on to that. Hold on to that for right now. Okay. So for the purposes of this, thinking about R squared as equal to eta squared, essentially. Okay. But what our F test here does is it tells us whether or not is our regression model predicting some non-zero proportion of variability in my outcome. Okay. So this is the test. Basically, this F here in my overall ANOVA, my null hypothesis is that population coefficient for R squared, rho squared is equal to 0, right? And so, Sally, what is this telling me about sort of as a test of my null hypothesis here?
That is not compatible with the null hypothesis?
Exactly, right. These data are not compatible with a proposed population coefficient of 0. In fact, it's 0.605. I mean, I've only got 24 people in this sample, but there's a strong association between X and Y here, right? So again, this is just a test of our overall model. This is our model predict variability in our outcome, right? If we have a large p-value here, say that's 0.5, Alicia, what would that tell us about our model? Yeah. It's consistent with the null hypotheses. In other words, it's no good. I dumped a bunch of predictors in there that had nothing to do with my outcome, and so I don't have a good model. Okay. So this is our ANOVA table. This is a test of my R squared, and then down here we have a coefficient table. Here I have my regression constant. This is my A. Okay. Chris C, how do I interpret this coefficient right here? My constant, yeah.
So is that your intercept?
Yep.
So it's if your, I forget what we were testing. Is this?
It's X and Y.
Oh, just X and Y?
Yeah.
Okay, there's not like okay. So if X is 0, then you would expect your outcome to be 2.78.
Perfect, right? I don't need to know anything what the variables are. What I do know is if my X is 0, I expect my Y to be 2.718. Sean, what about my coefficient here for X1?
So it's the slope. So if you have a unit change in X1, you would expect Y to change by 0.5.
Exactly, right? So So this is my unstandardized coefficient, this is my slope. For every unit change, based on my model, right? Every unit change in x should result in a corresponding 0.574 change in y, based on my model, right? Now we want to say, so if I increase by 1, we expect my outcome to increase by 0.57. If I decrease by 1, and if I decrease by 0.57, right? So this is what we've got in our unstandardized coefficient. Okay. Yeah.
And so are those rating benchmarks for significance because you're pretty sure they're not 0?
What's that?
Are those reaching significance because you're pretty sure that they're not 0?
Exactly.
Okay.
Perfect. Right? And my significance test, my hypothesis test is just saying, like, is this value 0? Okay. Now, is the hypothesis test for my slope important? Relevant? Yeah, right? Sometimes, depending on, like, but in general, right? This is just testing the unique effect of x on y, right? Is it 0? So we're kind of interested in that. But we also have a significance test for my intercept. Tomorrow is a significance test for my intercepts, tell me.
If we're predicting,
What's that?
like if we have a good prediction for between x and y.
Okay, so what is my intercept or my constant telling me?
For like 2.718,
Yeah.
it's telling you that when x is 0, y is 2.718.
Okay, so this is my expected value of my outcome when x is equal to 0. And I find that that's significant. What does that tell me? Anybody?
It's not 0.
That it's not 0, right? Is that relevant information? Most of the time, probably not. There are circumstances where it might be. But this test, again, so this is why you want to be able to, on your SPSS output, be able to identify if someone like, and my intercept was significant. Unless there's a reason that's exciting, like that just, it just says my expected value of my outcome when everything is everything is 0 is not 0. So there can be times when that it starts to become important, but for this, it's rare in this case, right? Okay, so we've got our unstandardized coefficients. We've got our standard error for each one of the coefficients. If we take my coefficient and divide by my standard error, what do I get? Yeah, you get my t statistic, right? You take that divided by that, you get that. That divided by that, you get that. These are 1 degree of freedom tests, right? So easy to go through and manipulate that. We also have a standardized coefficient here. What's the standardized coefficient? Sean? You're a regression master. Tell me what my standardized coefficient is.
It's the coefficient divided by the pooled standard deviation.
Okay. Practically, sort of, and I don't know, you may not have done this, but what's a practical interpretation of a standardized coefficient?
The standard deviation.
Yeah. Ignacio, so to elaborate on that. So I've got a standardized coefficient of 0.778. What does that mean?
So that means that it will change the 1 unit change of the independent variable will make to change the dependent variable 0.778 standard deviations.
Okay, almost perfect. When we're talking about our standardized coefficient, what is a 1 unit change in x for our standardized coefficient? A standard deviation, right? So this is saying, sort of based on this model, for every standard deviation unit increase in x, I expect a corresponding 0.778 standard deviation increase in y, right? Our standardized coefficients, the same thing as our unstandardized coefficients. It's just our units, in this case, are standard deviations, right? For every standard deviation increase in this, we have corresponding standard deviation in this, right? And we'll talk about how we go through and derive that sort of later on with models and things like that. Essentially, if we were to take these data and take x and create z-scores, and take y and create z-scores, and then regress the z-scores of y on these z-scores of x, my unstandardized coefficient would be 0.778. Okay, so we've got the expected value of y when x equals 0. Here we've got the expected change in y given the unit change in x in raw units, and then here our standardized coefficient is going to give us the expected standard deviation unit change in y given a standard deviation unit change in x. Yeah.
What if you were using z-scores as the outcome variable, and then did not for the other variable?
And now, there are situations where you might do that, right? And so how would I interpret my standardized or my unstandardized coefficient?
It would be one standard deviation change, or one unit change equals one standard deviation.
Exactly.
Okay.
And there's some applications in like SEM and stuff like that where that form of standardization starts to become useful. We don't see it much here. The main thing, but there's nothing wrong with doing that. If you wanted to set up your model that way and that made sense from a research question, that's completely fair. The units are semi-arbitrary, don't matter at all, right? As long as you know what your units are and interpret those appropriately, you're good to go. All right, so relevant formulas, my degrees of freedom for my regression is going to be equal to the number of predictors. How many predictors do I have in this model? 1. Standard degrees of freedom for my regression is 1. My degrees of freedom for my residual is going to be the total people in my sample minus the number of predictors minus 1. My degrees of freedom total is going to be the number of people in my sample minus 1. Got that. My standardized coefficient is just going to be my unstandardized coefficient times the standard deviation of x divided by the standard deviation of y. Okay? If I take this value and I multiply that by the standard deviation of x divided by the standard deviation of y, I'm going to get that. The standard error for my regression coefficient is going to be the standard deviation of y over standard deviation of x times the square root of 1 minus the square of my correlation of x and y over number of people in the sample minus the number of predictors minus 1. That's going to give me my standard error there. So pretty easy, straightforward in bivariate regression. Easy to go through and calculate this stuff by hand. Okay. Remember here that my standard error is an index standard error for my regression coefficients. Same interpretation as standard error for anything, right? It's an index of the stability and reliability of the sample statistic is an estimate of the population parameter. This is just saying, if I were, in a sample of 24, to regress x onto y over an infinite number of times in a sample of 24 from larger population, I would expect this regression coefficient to jump around by about 1/10 of a point on average, right? So just remembering sort of what standard error is and how we're going through and talk about it. Questions? Oh, yeah. My hypotheses here are that my null hypothesis is that my intercept is 0, that my regression coefficient is 0. That's what's being tested there. Okay. Stata, Alicia, here same thing. Sum of squares model, sum of squares residual, sum of squares total. There's my R squared, my unstandardized coefficient for x, my constant, right, hypotheses. Here's beta. So we're requesting a standardized coefficient. Here's my standardized coefficient. Same stuff as we got before. Okay. That's univariate or bivariate regression. And bivariate regression is, there's not much. It's rare to see a regression model just one predictor. I mean, essentially, my correlation or my standardized coefficient is just equal to my correlation, unless I'm interested in predicting some outcome with one predictor, and I need that regression equation to actually predict actual individual outcomes. I'm just going to go through and run a correlation on that and stuff, right? But what I'm doing with multiple regressions, I'm taking a set of independent variables to account for some variability in a single continuous dependent variable. So I'm still with my multiple regression. Still wanting to predict y. That's my primary objective here. But the contribution of my individual predictors is not only going to take into account their association with my outcome, but it's also going to take into account the correlation between the predictors themselves. Okay? And so what ends up happening is we get just taking that basic regression model that we worked with before, and we're just kind of extending it out. So we've got my predicted value of my outcome, plus my intercept, plus the weighted effect of x1, plus the weighted effect of x2, so on and so forth, however many predictors I have, plus my error term here. Okay. So, two predictor case. most basic form of multiple regression. I got my expected value of my outcome, predicted score of y. This is my intercept or my regression coefficient. Someone tell me what my intercept now here represents. What do you think, Nick?
When both of your predictors are 0.
Yep. Okay. This is my expected value of my outcome when all of my predictors are equal to 0. So if I enter 0 for x1, 0 for x2, that drops out, that drops out. The average of E should be, is by definition 0. So my intercept is the expected value of my outcome when all my predictors are held equal to 0. Okay. My coefficient for x1 is a partial coefficient of regression of xy on my y on x1 holding sort of this other predictor constant. Same thing, my second regression coefficient, partial regression coefficient of the regression on y on x2 holding x1 constant, okay? And this continues to just be my residual, the difference between my observed score and my predicted score. Okay? But what we see now when we start adding additional predictors into the model is that the magnitude of my regression coefficients here dependent on two different things. One, the association of, individual association of each one of these variables with my outcome, right? So the association of my predictors and my outcome determines this to some extent, but also the association of those two predictor variables together. That starts to play a role into the magnitude of my outcome, okay? So here, so I've got two predictors. My first predictor, my first regression weight, represents the unique relation of x1 with y after we suck out all the variability associated with x2, right? My second coefficient here, this is the unique relation of x2 with y after all the covariation associated with x1 is pulled out, okay? And so what we do is with our regression models, what we're doing is why I think it's important to talk about this is the unique effect of x on y, because we're parceling out shared variability with other things, okay? So our individual coefficients, it's not just the raw association of x and y, we're talking about the unique association between these predictors and the outcome, okay? So if I take the squared correlation, so here's x1, here's x2, and here's y, okay? If I wanted to take the squared correlation of x1 with y, right? And if I take a bivariate correlation and square it, what does this give me?
Your T? No.
No.
Your covariance? I don't know.
Common variation.
Common variation, right? If I say x and y are correlated 0.5, if I take 0.5 and square it, I'd say sort of x account. We talk about it in terms of causal, although we probably shouldn't. But the 25% of variability in x is shared with y. That's all it says, right? We're just taking that Pearson correlation and squaring it, right? So if I take the squared correlation of y and x1, shared variance, the overlap here is regions B and C. You can see that? And if I take the correlation of y and x2 and square those, that's C and D correlated with, that's the shared overlapping variance there. Okay. If I look at the correlation of x1 and x2 and I square that, that's giving me C and E. That's just the overlap of those ones there. Okay. But if I'm looking at the correlation, the squared correlation of y regressed onto 1, or of y regressed onto x1, controlling for x2, now I just have section B here. Why is that? Yeah, Chris?
Because you've taken out x2.
Yeah, x2 doesn't count. This doesn't count. x1 doesn't get any credit for anything that's shared with x2. So partial coefficient of the regression of y onto x1 in this situation just gives me B. C overlaps with y, but C also overlaps with x1, so that doesn't get counted. Okay. Same thing, the regression of y onto x2 controlling for x1 just gives me portion D here. Okay. This is what's unique. This is what x2 is bringing to the party, right? x2 brought buffalo dip and tortilla chips, right? But X1 also brought tortilla chips, right? That's C. No one gets credit for tortilla chips. Everybody bought tortilla chips. X2 does get credit for the buffalo dip though, right? So this is the unique association after we account for shared variability here, and then my R squared for my model, right? The regression of Y on X1 and X2, B, C, and D. That goes into my R squared, okay? CJ, does X1 or X2 get credit for region C in this regression equation, or in this regression model? No, it doesn't. But it's still variance that's accounted for in my outcome, right? And so what we see is that C gets caught up in my R squared, right? That's the total variability in my outcome that's being accounted for. But my individual coefficients, my regression coefficients for X1 and X2 are just getting accounted for individually with that. Questions about overlapping sort of partial coefficients with this? Okay, so this is just regression formulas here. So my standardized coefficient of regression of Y on X1 controlling for X2. This is a correlation of Y with X1 minus the product correlation of Y with X2 and Y with X1 over 1 minus that, right? Same thing for partial correlation of Y2 controlling for X1. My unstandardized coefficient, so small b is unstandardized coefficient, beta is your standardized coefficient. My partial coefficient here, or my unstandardized regression coefficient, is just equal to my standardized coefficient multiplied by the square of x, or the standard deviation of y over the standard deviation of x. My r squared is just the sum of squares of regression over the sum of squares of y. Or if I went through and I had my y value, my outcome, and then I created in SPSS a column, a variable that was my prediction, and correlated it with my observed value and squared that, it's also going to give me my y squared, or my r squared. So in this situation, my unstandardized coefficient for x1 here, we're going to interpret this as the expected change in y given a unit change in x, holding all other predictors constant at 0, right? So controlling for all other predictors, this is my expected change in y given a unit change in x. My standardized coefficient here interpreted as the expected change in standard deviation units of y given standard deviation change in x, holding all other predictors constant at 0, right? So basically, we're saying controlling for other variables in the model. I would expect a unit change in x to result in an expected change of x amount in y, holding everything else constant, holding everything else constant at 0. And if we're talking about our standardized predictors, standard deviation unit in x is expected to hold result in standard deviation unit change in y, holding all of the predictors constant at 0. Okay? So we're parceling things out. So as we go through, and as I'm getting increasing overlap between my predictors, let's have a regression model, CJ, that has a bunch of correlated predictors, like heavily correlated predictors. Even if x holds a strong relationship with y, am I going to get a strong coefficient in my regression model? Why not?
Because you have those other predictors covered for it as well.
Because there's a lot of overlap. Everybody brought chips to the party, right? It don't matter if I brought a truckload of chips, 4 pallets of chips to the party. Everybody brought chips to the party. I don't get credit for any of that stuff because it's shared. It's only the unique stuff. And this is where we get into issues with collinearity, right? If I've got a bunch of predictors that are all stacked on top of one another, I can have very, very strong bivariate correlations, incredibly strong bivariate correlations, and then that predictor has no unique association with it. I haven't, my hypothesis test will say, no, I don't have this isn't a meaningful predictor in my model because everything that it shares with y is already accounted for by everything else. And so functionally, even though there's a strong bivariate correlation, it's not a useful predictor in this model. It's redundant with other things that I have. And that gets into some collinearity stuff we'll talk about later on down the road. Okay. Yeah.
So this just becomes a bunch of ANCOVAs run over and over again, similar to the bivariate model.
Yeah, ANCOVA is just a regression model. Okay. And so this is why, we put in a lot of time talking about ANOVAs and things like that. And ANOVA is a nice way to go through and think about things. If we have categorical variables talking about mean differences and things like that, but essentially an ANCOVA is just a regression model. Questions? All right, cool. So we're in a good spot. We're a little behind, but that's fine. It was going to happen eventually. Actually, not too bad. Where are we at? Yeah, we're getting close. All right. So what we'll do next time, we'll start off with quiz. So make sure you go through, read chapter 4, take notes. Don't worry about formulas, just making sure conceptually you've got a handle on this stuff. We'll spend the first hour of the class on Wednesday working through that, and then we'll jump back into regression and roll forward on this. We've got a lot of regression stuff to cover before we'll have our first problem set, so you'll have time to work on the repeated measure stuff in the background. Make sure you're working with your group, get together, everybody work together on the same, don't section things off, because you'll be worse for the wear out for it. But if anything comes up, let me know. Okay, awesome. Thanks, everyone.